Hi everybody, it's Mr. Zarzak here, and in this screencast I'm going to review some important concepts for direct current. Alright, so let's take a trip. Alright, last unit we introduced the idea of capacitance and a capacitor. This unit we're going to put them into circuits. So a useful way to think about capacitors is in terms of their energy. Okay, energy stored in a field. What do I mean by that? Alright, well, as we add charge to our plates, okay, the more charge that we build up, the stronger the electric field. And the stronger the electric field, the stronger the voltage between the plates. Remember, the slope is just the field, so we are making like our slope steeper, 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 okay, and higher, 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 higher. Okay, it turns out that for a uniform field like this, we get a nice relationship between voltage and charge. So like if I were going to plot a graph of how the voltage on a capacitor changes as we added charge, okay, what we would find is we would get a relationship that is linear, okay? More charge on the plates, more change in voltage. Great, so what? Well, whenever we have a graph, our two basic tricks in all of physics is we look at the slope or we look at the area. So if we looked at the area underneath the graph, okay, it's a triangle, okay, and we could do this with calculus, but it's a triangle, okay, so we know how to calculate the area of a triangle. It's half the base times the height, okay, or actually, I'm going to write it as half the height times the base. You'll see why here in just a second. Height times the base. Okay, well, what's that all about? All right, well, if we take it aside here for just a moment, all right, all of our study in voltage really came from the idea that voltage is electric potential, or the electric potential energy per unit charge. So like here, so change in voltage is the change in potential energy per charge, right? Okay, so then we take that and we say, all right, great. Well, then the change in potential energy is just the change in voltage times the charge. And the change in energy, hey, that's just work, okay? So point is like, look, change in voltage, charge. Okay, if we multiply change in voltage times the charge, we're getting back to the change in potential energy, all right, or the work done on a charge to give it potential energy. All right, so anyway, so going back to our little formula here, the underneath we've got a triangle is half base times height. Well, half height times base, sorry, that's the change in voltage times the base, that's the charge. Okay, and look, that tells us how the potential energy changes as we add charge to our plates and the voltage increases on our capacitor. It just follows this relationship, okay? It's just a linear relationship, so it's just think like, way back with like springs, like Hooke's law, force is equal to kx, okay? That force follows this relationship that's based upon the stretch. Okay, well here, our potential energy follows this relationship based upon the capacitance of our capacitor. Okay, we just build it up like this. So that's kind of cool that it does that, all right? Well, so what? Well, we can take this and we can play around with this a little bit. All right, this could be useful to us, as like the basis of an equation. All right, we'll call this like version number 1. Okay, well, we can also take and we could take advantage of the fact that, well, last unit, all right, we defined capacitance, all right, as just the charge per the change in voltage. All right, so if I just take that and I rearrange it, so I can say capacitance times the change in voltage is equal to the charge, all right? And so then if I take my original relationship here for potential energy, okay, and look, I got two that contain Q, so let's just sub out, that Q and throw in capacitance times the change in voltage. So I get half times delta V times C times delta V, which means I get another version of this. Change in potential energy is equal to 1/2, let's see, so we'd have C times the change in voltage, so CV squared. That's another way I can get to energy by knowing capacitance and voltage. But wait, there's more, all right? We could also write this, all right? We've done this kind of trick before too, so let's see. So capacitance is equal to charge over change in voltage. Capacitance times change in voltage is charge. So let's write this as the change in voltage is equal to the charge per capacitance. Okay, and again, we're just going to take our original little relationship here, and let's replace that change in voltage, okay, with this right here. All right, and so what do we have left here? I'm going to have to sneak this over in the corner because I'm running out of room. Wait a minute. No, I refuse. I'll put this over here. Go over there. And be simplified. The change in potential energy. So let's see, what do I got here? I got Q squared over 2C. Hey, look at that. Okay, so 3 different ways, all right, we can talk about this energy of a capacitor. All right, now, is any of this stuff on the equation sheet? Well, sort of. Okay, so on the AP equation sheet, the thing that we have to be careful of, all right, is that, well, one, potential energy, they like to use, if you remember, U, okay, because potential energy starts with a U. Right. Okay, you'll actually see 2 different potential energy equations on the electricity and magnetism side. You'll see the one that's for the potential energy of an electric field. They write it like this. Okay, what are we staring at here? We're staring at this. The change in potential energy is equal to change in voltage times the charge. That's not for a capacitor. What about for a capacitor? The energy stored in a capacitor, and these are not V's, these are U's. Okay, sometimes the script doesn't have that little piece there. All right, you will see this. This is what's on the equation sheet. Q times delta V. Okay, so again, energy in electric field, okay, comes from change in voltage times charge, and then energy stored in a capacitor. So those are both possibilities or things that can be useful to us. Just make sure you understand which equation you're using for which application. The C one goes for capacitors. Okay, and these are just different manipulations, kind of like we do with the power equation, which I'll touch on here in a couple of slides. All right. Current. Okay, we've been using current. We're writing equations for current. What the heck is current? It's the change in charge with respect to time. Okay, it's the actual charge flowing through a conductor, or I guess an insulator too. If we push hard enough, we can push current through anything. All right, it's the change in charge with respect to time. So the dq dt, okay, would be the differential way of writing that. Okay, an ampere or an amp is defined as a coulomb per second. Okay, I have a really complicated example here. It says 2 coulombs of charge pass through a resistor in 1 minute. What's the current? So then the current is just the charge, okay, in the time frame, but we have to watch out for this is 1 minute, so this would be 60 seconds. Okay, so 2 over 60 is something, it's that. Okay, great, so it's 0.033 amps. All right, there we go. All right, we know the cross-sectional area. All right, we can get a measurement of the current that flows through it with respect to time. All right, if we know the cross-sectional area. We'll come back to that in a minute. All right, something else you'll see. Okay, when we build batteries, remember we talked about internal resistance of the batteries and all that fun stuff. Okay, well, one of the other things that we can do when we engineer is well, how much voltage do we get out of the battery? How do we do that? With materials, by physically building batteries. We don't go very in depth in this in physics. Okay, for more on this, get a job working in the battery field, specialize in college, take AP Chem. They go much more in detail. All right, we talked about that EMF, okay, or the cell potential. Okay, that's kind of what this relates to here. All right, when we're trying to get that EMF, okay, or that cell potential, all right, it has to do with how we manufacture the battery. Okay, so then we pick different materials, and different substances, when we manufacture them, will provide us with different electric potentials. So this would be something that AP could potentially throw at you. Okay, they could give you a table like this and say, look, these different substances, okay, provide these electric potentials. So we make these, these different electrodes, these little rods, or these little thin pieces of metal that we put into some kind of solution. And when we do that, they provide this much potential. How do we build batteries out of them? Well, batteries have 2 terminals, a positive and a negative terminal. Okay, by our current convention, thank you, Ben Franklin, all right, charges flow from a lower potential to a higher potential. Okay, so let's say we wanted to get a certain voltage. All right, well, we pick the materials that will get us the voltage that we want. So what do you mean? Let's say we built here, let's just go on the 2 ends of the scale. Let's say we did a lithium and gold. So we're going to manufacture Okay, a battery with 2 electrodes, one with gold, one with lithium. Okay, so what? What's the voltage? The voltage. Okay, the change in the voltage across the potential, the cell potential. All right, as you take your 2, delta means subtract. Okay, final minus initial, final minus an initial. Okay, the charges will go from the lower to the higher potential. Okay, that's by the way we define our current. So the higher one is a plus 1.3. Okay, the lower one is it minus 3. Okay, so for these electrodes, if we put them together, okay, we will get a potential difference, an EMF of, let's see, 1.3 minus minus, so plus, so it'd be 4.3 volts. Great, so if you manufactured a gold lithium battery, we'd get a cell potential of 4.3 volts. There you go. All right, I'll do another one just to kind of emphasize, okay, that when we define our direction of current flow, it's from the lower to the higher potential. Well, now wait a minute. What if you did like a silver and gold? Let's just try to make the most expensive, ridiculous battery that we can think of. Okay, well, silver has a lower electrode potential than gold. All right, but it's positive. It doesn't matter. It's from lower to higher. Okay, so like if we did this for our gold-silver battery, the change in voltage, okay, if we'd end up at the positive 1.3 from the positive 0.80, in which case we get a potential difference of, what is that, a half. You get half a volt. So I guess you could build a gold-silver battery, but it would be really expensive and you wouldn't get much voltage. So why would you do that? I don't know. Okay, but typically we don't. We could. We wouldn't get much voltage. That's about the extent, okay, for the material science aspect that AP is going to ask you for these kind of things. All right, but there's tricky stuff in here, and that's what AP does, is ask you tricky stuff. Simple but tricky. Okay, why did copper do that? Well, because when I copied over this file, it just got shifted, so there's no real good reason for that. Moving on. When studying Kirchhoff, okay, we had different voltage sources connected in all kinds of crazy ways in series and parallel. Okay, can we do that? Yes, we can. Why would we do that? Well, because we're trying to either change the voltage or the current. Okay, so if I take batteries and I put them in series, the voltages add. They maintain the same current. So like, I'm gonna draw a picture of a battery. There's my little AA battery with my little positive terminal and my negative terminal. Okay, if you've ever changed the batteries like on a flashlight, a lot of times you have 2. Okay, and they get put back to back like this. I could have them overlap. It's just gonna look weird. And it's like, oh no, that's not right. Okay, so whatever. You just line them up like that inside the flashlight. Okay, why are you doing that? Well, because you're putting the cells, you're putting the batteries in series. Why? So that you get a higher voltage. Why? Because, well, sometimes the voltage requirement of your light bulb is higher than the 1.5 volts that you typically get in a battery that you buy in a store, like a AA. Okay, so that's one way you can connect it. Careful, a lot of times if you've changed batteries, they'll take an inside the battery pack. Okay, it will look like that the cells are in parallel. All right, now we can't put cells in parallel. The reason we would do that is you get addition of current. I'll talk about that in a minute. Okay, when you load batteries, okay, they'll put like, oh, the batteries are side by side, so they must be in parallel. But actually, a lot of times in battery packs, okay, when you actually insert the batteries, you ever notice that the batteries are inserted in, they alternate like this. Okay, why do they do that? Because they're trying to trick us. No, okay, they're just trying to fit the space that they have to work with. Okay, these are actually typically they're in series, and what they'll do is they'll put little conductive paths, right? Like, you know, so then there'll be like a little nub and then a piece of plastic, but there's actually a conductive path that then connects to here. Okay, and then a lot of times they'll put like a little like spring or something over on this side. It doesn't matter. It's just a conductive path that connects the positive terminal one to the negative terminal another, and then there's like a little nub over here that the positive terminal touches, and then there's some plastic, but there's a conductor inside there that goes to this. Okay, so these actually wind up being in series with one another. Okay, and then for the device, well then like, oh look, the positive part connects over here and it goes off to whatever you're trying to power. Okay, and then here's the negative side. Okay, so that's actually typically that's in series. Can you put things in parallel? Yes, you can. Okay, why would you do that? All right, well, things in parallel have the same voltage drop across, so then why would you do that? Because then the current's add, so you can spike the current. Okay, great. When you put batteries in parallel, okay, what you never want to do is you don't want to mix batteries like I've done here. Okay, so why don't do it? Okay, so let's do it. Why don't we want to do it? Okay, well here, so we have like a 12, so like this would be like this one's 12 volts, okay, and this one's 6 volts, and this one's 6 volts, okay, and then this thing over here, that's our load. We're gonna like that's our light bulb for our flashlight, or whatever our device. It's the load. Okay, actually I'm not really interested in that. Okay, we don't want to do this, all right, when we do that, because typically what happens is the battery that's at the higher voltage, okay, is going to try to charge or push current into the lower voltage. How do we know this? Well, Kirchhoff tells us, okay, so like, it's a circuit, there's a bunch of loops, so I could make some loop equations, all right? Forget about the load, let's just focus on these two. Let's just focus on these here in the center, all right? Well, if we draw our loop, okay, and like, well, how do you know the loop goes that way? Well, it's the higher voltage, so like, just from experience, I know this, but it's a complete loop, which means that the voltage rise and drops have got to add up to 0. So like, well, wait a minute, I have a 12 volt rise over here, which means, in this part here, which means I got to have a 12 volt drop over here. Well, what's that about? This is only 6 volts. Like if I do 12 minus 6, because like the positive terminals match up, so I got 12 volts minus 6 volts. That does not add up to 0. What's going on here? Well, batteries have internal resistances. Okay, and like the 12 volt would have one too, but there would be some internal resistance inside this thing. Okay, and the other 6 volts would get dissipated. Okay, so you'd get some current that would flow into this. Like my current would flow into this little internal resistance. Okay, I'd have to take care of the other 6 volts. So you'd actually be pushing current back through this thing, which if it's a rechargeable battery would recharge it. That'd be a good thing, but if it's not, it just means it's going to heat the battery up a whole bunch and it's going to waste a bunch of energy. Okay, so like I said, when we put batteries in parallel, we don't want to mix voltages. You got to keep them all the same so that doesn't happen, so that the current's going where you want it to go, which is into your load over here. Power. Okay, we've seen some of this before, so the derivations just come from Ohm's law. Okay, so like, so if we take and we sub in voltage is current times resistance, we get this I squared R, or we can take V over R and set it equal to I, and then sub it in, we get this V squared over R, okay, version of power. So we've kind of seen that stuff before. The things that I want to make mention of, okay, is AP likes to ask questions like, oh, here's a circuit, and you double the voltage. What does that do to the power? Okay, and the easy answer that is wrong, of course, because it's AP, so they try to trick you, is, oh, double the voltage is double the power. That's not correct, okay? The problem with this is if you double the voltage, pick a color. Okay, well then what happens is for a current or for a circuit that has the same resistance, you wind up doubling the overall current too. So, you wind up like 2 times 2, so you get like 4 times the power. How can this be? Well, doubling the voltage has the effect of doubling the current. So like, look, 2 squared is 4. I know my handwriting is really pretty, but you know how to do 2 squared, or just double the voltage. 2 squared is 4. Okay, so that's one thing to watch out for. Like, oh, if you triple the voltage, you triple the current, you get 9 times the power. Okay, so that's one thing to watch out for. And then something else, this is just kind of interesting. Okay, I'm always talking about like engineering kind of stuff. All right, when you look at high voltage power lines, so like the really big, tall towers, right, like that transmit, energy over really far distances, electrical energy, okay? They're high voltage towers. Why are they high voltage? Okay, well, that has to do with what happens during the transfer and what happens when we build. All right, when we build, those big cables are made out of aluminum. Okay, aluminum is chosen over copper. Okay, the reason, number one, it's cheaper. All right, typically then copper is more expensive. Okay, great, that's nice. But then maybe even more important, it's lighter. Okay, so for, a meter of aluminum, okay, at some thickness is lighter than a meter of copper. It's less dense, I guess is the right way to say it. Okay, well, why does that matter? Well, when you're running these things between, big giant towers, you want to separate those towers by as much as possible because nobody wants to see them and you have to build them. Okay, so you can get towers that are farther apart by stringing wires in between that are going to be lighter. Okay, so that part is kind of cool. It's also cheaper. All right, so you're saving money. You can put your towers farther apart, which means you need less towers, so it saves even more money, and people don't typically like the towers, so not as many to look at. Okay, so that's all the upside. The downside, aluminum has more resistance than copper. That's the downside. Okay, so if there's more resistance, well, that means when you transmit, okay, for the same current, if you've got more resistance, okay, well, then more of that power is going to get wasted as heat. Okay, we don't want that. All right, we're going to minimize that. That's energy loss. I'm not stringing wires through the air to heat the air up. Okay, I'm trying to send energy, electrical energy. Okay, and so what we do is we broadcast that power. We send that electricity at extremely high voltage to keep the current down. All right, I mean, here's the relationship, right? So like we're going to transmit some amount of energy per time, right? It's energy per time. So for the same energy per time, for the same power transmission, a really high voltage yields a lower current. And well, a lower current means you're going to get less overall heat generated in the wires because it's that current that's pushing through the wires that ultimately generates that thermal energy. Okay, so that's kind of fun fact. All right, why does that happen? All right, well, it has to do with this. I'm kind of skipping around here. I'll come back to the previous slide in just a second. Okay, we've touched on this as well. When we apply a uniform electric field to a wire, okay, it gets charges going. I remember, like, electric fields force on a charge, okay, but there's interaction that occurs within the wire because, well, there's atoms, which means that there's protons and electrons. It means there's charges already there, even in the neutral wire. So along that path, you get these little local interactions that will cause our charges to go all over the place. Okay, now the truth is, well, this is not a correct model of the atom. There's no correct model of the atom. Okay, they're all just models, so get over it. Okay, and take your electron density clouds and probability and all that stuff, and, like, I get it. Okay, stay with me. Negative charges are actually what move in the wire. Okay, the effect of that, applying a uniform field, induces that motion, but because of these little local interactions, like all these little atoms have protons and electrons, so they all have their own little local fields. So the electrons that do move, they kind of get pushed around all over the place. And it's over time. See, so like I've just drawn out one hypothetical path here, okay, that this thing might actually follow. Okay, now there's a net effect. Okay, so like it started here. What is the color that's going to show up on this? I have no idea. I need a color that's going to show up on this. It started here, okay, and then sometime later it's like over here. Well, we're just trying to send the charge through the wire. Remember, like, current is based upon our direction of positive charge flow, when in reality it's electrons. Okay, well, it's like the electrons over time go this length. Okay, that's the drift. Okay, how far they actually go every second. And even though these electrons are bouncing around at nearly the speed of light, okay, their drift velocity is really, really tiny. Okay, it's on the order of, fractions of a millimeter per second, teeny, teeny, tiny. All right, but as long as we can get them to have a net motion in the direction that we want them to, we've got ourselves a current. All right. Well, anyway, so kind of backing up here. All right, the way that we measure current is through this concept of current density. If you think of like Ohm's law, right? It's like charge density. That's for the static case. What about the not static case? When the charges move, we have current density, the motion of charge through some area. All right. So this current density, that's that J variable. Okay, and it's really just a matter of how much current that we get that flows through some cross-sectional area. So like, for a wire, here, back up a couple slides here. Okay, well, in the cross-sectional area that we're talking about, like, oh, how much current is flowing through that little slice? Okay, and then based upon the gauge of the wire, we can have like bigger wire or thinner wire, all right, depending upon what we're trying to do in terms of the current. Okay, great. Come back to this. What if the thing we're moving the current through, what if that conductor is not a pretty area? What if the area changes, okay, as you move through it? Well, the constant is the density. Okay, the variable would be the area, so you deal with that changing area. You do calculus if you need to. It's like if we tried to push the current through the spoon, we're like, oh, the cross-sectional area looks like that, and it gets a little thinner, and then it widens up, and it's like concave or convex, depending on what you look at. You need some function to describe that. Luckily, this doesn't really come up on the AP test. Okay, I can't remember a time we've seen a case we have to solve this. It's just like, hey, we can do calculus. So here it is, just so you can see it. All right, so what does show up? Okay, well, like, remember over here, okay, this, man, I need a color that will show up. That little chunk right, that's the length, okay, of the drift per second, okay? So we can define this drift velocity of charges as just the length that they travel along our conductor with respect to time, okay? Great. So then if I write out this relationship, all right, so there's our little velocity part, okay? That's this A, that's the cross-sectional area, all right? This here, this is charge, okay, and then this is just the charge density per volume. Okay, I know that's kind of gross. Just bear with me. Okay, it's going to be easier if we look at this in units in just a second. We're almost done. Okay, charge density per volume. Okay, if I take length times volume, so think like with a box, like length times width times height. Okay, well, like width times height, that's like the area of a rectangle. If you multiply it by how thick it is, then you've got the volume. Okay, so this is another way we can think about volume. Excuse me. All right, well, look, we've got two things that contain time in it. Okay, so I just rearrange them both to say time equals. So then for up here, what would that be? That'd be time is equal to L over velocity. Fantastic. Okay, and then for this mess over here, we'd have, what would this be? This would be time is equal to mess over current. Great. Two things. Set them equal to one another. That's what this is. Okay. Set them equal to each other. All right, and we can cancel some stuff. There's some stuff. Okay, what's left? We got 1 over velocity, so flip it over on itself. All right, and we wind up with this, okay? The drift velocity of charges is equal to the current divided by the charge density per volume times the cross-sectional area times the charge. Ugh. It's actually kind of useful, okay? Now, the way that they're going to put this on the AP equation sheet, okay, it looks like this. All right, and this is what we're going to dissect since this is what I saw on the equation sheet. So just think like essentially they're just taking this and they're moving it over there. Okay, the Nevada equation, okay, it looks like people from Nevada and people not from Nevada who typically say Nevada, okay, got in an argument, okay, and they decided to settle it by just taking out part of the name. That's the Nevada, no Nevada, no Nevada. Okay, I digress. Okay. I is current. Okay, that's coulomb per second. Okay, great. What's this other stuff? Okay, so this N, okay, that's just a count. What do you mean a count? So it's like the number of charges, okay, in a particular area. Right, so just think like number of charges in some space. I said area, I should have said volume, excuse me. Some number of charges in some space. Okay, this E, okay, that's the charge on an electron. So it's like 1.6 times 10 to the negative 19th. So it's charge on electrons. Its point is 1.6 times 10 to the 19th coulombs. Okay, then we have this term here. That's the drift velocity. All right. So drift velocity, what the heck is that? It's how fast the things are going. So it's just how much length they cover. So meters per second. All right, then there's that mess. Okay, and then there is this area thing. How do we measure area? Meters squared. Okay, so if I start putting this disaster together, oh my goodness. Okay, what do I get? Let's see, so number of coulombs. So that's just the number of charge. All right, then I've got meters and meters squared. That's meters cubed. So then, goodbye. So what's left? Current. There you go. That's Nevada. All right, so it'll pop up every now and then. It's on your equation sheet. Just be aware of like what it's trying to tell us. Like I said, it's a plug and chug. It's not that big a deal. Okay, anyway, so that has been your DC review. What's next? A more in-depth explanation of charge density. This is from Hyperphysics. .org. Okay, the charge density stuff is quite quite frankly, honestly, beyond the scope of this course. If you're interested in going into having a more in-depth understanding of the Nevada equation, then go to Hyperphysics and you can look it up and read through this all yourself if you want to, or you can take AP Chem too, because they get into this a little bit heavier. But that's it for us. Okay, read it yourself, learn about it if you're interested. Great. All right, we've got more important things for our purposes to move on to. Capacitors. That's next. All right. So this is Mr. Zarlik saying thanks for watching. I'll see you next time.